Alright, welcome to Chapter 3, Section 2 for Math 330. We're going to do nth ordered differential equations. So how do we solve nth order differential equations? Well, we're going to use some of the same techniques we did for second order. We're just going to increase the number of derivatives. So this is our standard non-homogeneous non-constant coefficient second order differential equation, and we can turn it into a homogeneous differential equation if the function here f of x is equal to 0. So what we're going to do is increase the number of derivatives until we have nth order, and then we have our polynomials in front of those. So we have our standard nth order non-homogeneous differential equation, since this is equal to f of x or some function of x that's not known at this point. So how do we handle these nth order differential equations? Well, we do the same thing we did before. We want the coefficient in front of the highest order derivative to be 1. So I'm going to divide the whole equation by this polynomial right there, and you do that, we get this non-homogeneous differential equation. And of course, there is a homogeneous linear equation associated with this one, and we can get it by making this f of x 0. And so this is the homogeneous differential equation. And you guys actually know how to solve this. This will be a polynomial. If you use the characteristic equation, this will be a polynomial of order n. So we would have n roots to this polynomial equation, and we would need to solve for those n roots. So how do we solve for them? Well, we have to use the principle of superposition for homogeneous equations. So if we have this homogeneous equation just here, what I'm going to say is we have n solutions. I'm going to call them y1, y2, all the way up to yn. And each one of these individual y's is a solution to our homogeneous linear equation on some interval I that we're interested in. And then I'm going to say if we have n constants here again, then I can combine all these constants in a linear combination so that y is also a solution to this differential equation up here. So basically what we're going to do is, like we did for a second order, we would have two solutions, and we combine those two solutions to get another solution. We would do the same here, except we don't have two solutions. We have n solutions to our differential equation, so we have to combine them. So basically we're just increasing the number of roots we have with our characteristic equation by increasing the number of derivatives in our differential equation. So how do we find these constants, C1 and C2? Well, we have a homogeneous differential equation right here, and we have three initial conditions right here, and what are claimed as three solutions to the differential equation. So the way we create it is I create an equation y by applying the principle of superposition. And now to find C1, C2, and C3, I need to apply the initial conditions. So I'll need the derivative of my y, and I'll need the second derivative of my y. Now that I have them, I can plug the first initial condition, which is this one. So y at 0 needs to be equal to 1, and all the x's get to be are 0, so we get this expression. I do the same thing for the derivative, so here's the derivative initial condition. I plug that information, I get this equation, and then I do the same for the second derivative, and I get this expression. So I have three unknowns and three equations. You can solve this. You should be able to solve this. And if you do that, what you'll find out is the values is C1 is 4/3, C2 happens to be 0, and C3 happens to be a negative 1/3. So our solution to this third order linear differential equation is this. This is solution. Now you can always check the solution by plugging it back in to here. We would need its derivative, its second derivative, and its third derivative. You plug it in here. It should all add up to be 0 if it's a solution. All right. How do you guarantee that the solution is unique and exists? Well, basically, in order to do that, all our coefficients and our f here, all these p of n's, p1s all the way down to p of n, need to be continuous on some interval I containing a point A. Then, given that the n numbers of initial conditions for the nth order differential equation, you will find a unique solution. It's only one solution, but you have to have n initial conditions here. So basically, if you have an nth order derivative, you have to have an n differential equation. So a second order differential equation, we had 2 initial conditions, these 2. So a third order, you're going to have 3, so on and so forth, all the way out to the nth order differential equation, where you would have to have n initial conditions. And if we have them, we get a unique, that is, one and only one solution to this differential equation on some interval I that satisfy these differential equations. Now, the maple activity you're going to have to do is, depending on the initial conditions that you apply, what are the family of solutions that will exist.
All right, so now that we have, we want to solve this nth order differential equation, we're going to have n solutions, and we need to determine if they're linearly dependent functions or linearly independent functions. To do that, we're going to do the Wronskian again, and as we go over the Wronskians, the difference is going to be, instead of being a 2 by 2, we're going to have an n by n, since we have n. The solutions will have an n by n determinant. And then I'll show you how to do an example here. The example we're going to do is problem 1 on page 170. It's a 3 by 3. It's probably not page 170 anymore because that's the old edition. So here's my function. First function f is 2x, g is 3x squared, and h is 5x minus 8x squared. And I'm going to create my determinant here. Remember, the first row is the functions themselves, f, x, and h. The second row is the derivative of those functions, and the third row is the second derivative of those functions. And now, to get to the determinant, I need to apply a technique called Cramer's rule, or the cofactor technique. To do that, I'll cross off my first my first row and my first column, and that crosses out the 2x, and then I'm left with this 2 by 2 determinant that's left over. So I get this value, I get 2x times whatever in here, and then I'll move my line over, and I'll cross out the first row, and my second column of that is a 3x. Now, since this is my second column, that's a minus. So it starts out being plus, the second one's minus, the third one would be plus, the fourth one would be minus, so on and so forth. That gives me this factor times this cofactor. And then I'll do the same thing for the third one. I'll cross out the first row and the third column. That leaves this as my multiplication factor. And since it's the third one, it's plus. I have this cofactor, whatever left here. And now I need to find my determinant. So I'm going to have this one times this one. So I have 6x times a minus 16. I'm going to have 6 times a minus 16x. And so I'll have this number, multiplication, minus whatever this is. It's the same thing. It's 0. So this term is 0. I'm going to have a 0 times 16, which is 0. A 0 times 5 minus 16x, which is 0. So this thing will be 0. I have 0 times 6. I have 0 times 6s, so that's 0. So the whole thing is 0. So these functions are not.
All right. So now, what do we do if we have a non-homogeneous differential equation? That is, so what we're going to do is I'm going to claim I have this solution called y of p, which we're going to call a particular solution. And that actually solves this non-homogeneous differential equation. So on this open interval I, where the functions of pi's and f are continuous, then we're going to let these y function here be linearly independent solutions of the associated homogeneous differential equation. So the actual solution to this non-homogeneous will be a sum of the homogeneous solutions plus the non-homogeneous solutions. So these homogeneous solutions right here have a name. They're called the characteristic, or the, sorry, not the characteristic, the complementary solutions to the associated homogeneous differential equation. So that is, if we eventually will learn how to solve this, find what our y of p should be based on this equation. But we're not to that point, but we can verify a solution. What we have is this differential equation, these initial conditions, and this complementary solution. So that's the solution to the homogeneous differential equation. And this is the solution to the non-homogeneous part. So what we're going to do is add them together, and that has to be a solution to this differential equation. So we need to find C1 and C2. Well, we do the same thing we did before. I evaluate the initial conditions for y. This is 0, this is 0. So I get just C1 times cosine of 0, which is 1. So basically we get C1 has to equal 2 in this case. So now I know C2, so I put it in here where I know C1. So I put in here and I took the derivative of our solution here. And now we're going to evaluate it at this initial condition. So that's going to be 0. And I'm left with this. I solve for C2. I get minus 5. I plug them back in here. This is our unique solution for this differential equation. Well, I hope you enjoyed this podcast. We'll work some more in class tomorrow. I'll see you then.